Hi there, Esther. This is page 2. Let's take a look here. So as a general rule, always draw what's being talked about. So we have an angle GUM. We aren't told whether it's acute, right, or obtuse. And whenever I'm working on a worksheet, when I account for stuff, I like to cross it out. So I drew an angle GUM, so I cross it out. Bisected by UT. Sweet patch, sweet patch. And I got that information. And here we have GUT, 8x minus 2. TUM is 2x plus 10. Ask you to solve for x. Well, what we know to be true here is that the angles are of equal measure. So then you can go like this. One angle equals the other angle. Now it asks you just to solve for x. I would never just ask for x in my class because it's super easy to check this. Whatever your x is, plug it back in, check the measures, and if your x is correct, those two measures would be equal. So just for good measure, always plug it back in and double check it. You have a segment CD, and it says P is between. Between does not mean middle. Once again, it means offset it. And we have C to P. I always like to use colors and brackets. X plus 14. And P to D. 2x minus 1 equals C to D, 34. So I usually like to talk about things before I talk about algebra, and I know the distance CP plus the distance P to D equals CD. I call that a thing equation. You talk about things, and then you talk about algebra. Once again, the question only asks for x. I would never do that. Once you solve for x, plug it back in, and you'll see that everything should fit together. It asks, what is another name for line BE? So BE is that line. Any 2 points name a line. So that could be called something like BD or DE even. So any 2 points. Which ray is the opposite of BC? So BC is this way. Opposite means going the opposite direction, and the opposite ray would be BA. Here we have an angle, TOC. And interior does not mean bisector, so I'm going to offset it so I don't confuse myself. And here we have KOC. TOC, and then TOK, solve for x. And then it wants to explain your reasoning. Your reasoning is going to include this simple concept. One small angle plus the other small angle equals the larger angle. And the super fancy name for little angles add up to big angles is called angle addition. Wow. Yeah, so complicated, I know. And then you just plug it in. Once again, it asks just for x. I would never do that. Take the value of x, whatever it is, plug it back in, and you will see how everything fits together accurately. It says write a 2-column proof. Let's start with our given information. When I do proofs, I use this process. Mark the given, mark the implied, mark what I call freebies, and then talk it through. Freebies are things that are true even if it's not in the given. Let me give you an example. You are given that U is the midpoint of MG. So I'm just going to trace MG here. Use the midpoint. And you are told that M to U is 8x minus 5. And U to G is 6x plus 13. And you're trying to prove. Prove just means explain. Don't get all into that. Explain why x equals 9. That's what we're going to try to do. So we have our given information. Implied and freebie. What else do you know is true? Well, just kind of make yourself a list. What's implied is the fact that MU must equal UG. Why? Because you have a midpoint. That's what would be something implied. Freebie would be something like this segment adds up to this segment plus that segment equals the big one. Usually proofs, you just want to take a moment and just mentally talk it through. And obviously you're going to solve for x here. And obviously because of the midpoint, you have things that are equal. And if you solve for the x, it's pretty easy to see that it's going to end up being 9. So we'll do this one together. Traditionally, we have something called this, statements on the left. I think of that as how, like what are the steps? And then we have reasons here on the right. Okay, so I'm going to start by writing. I think we're going to need more space here. I'm going to take this information right here. I'm going to pop it onto a new page. There we go. How do you get to the answer? X equals 9, that's what how is, statements. And then why is each step legal? There's your why. Number 1, we're simply going to say U is midpoint of MG. And the reason why, it's given. So logically, what's logically true because of that is the fact that the distance of mu equals the distance of ug. Why is that true? That's called definition of a midpoint. Why didn't I do all the givens right off the bat? You could do that quite easily. So there's no particular order that's absolutely required. You just have to ask yourself, how do you get to that point? So step number 3, I know mu equals 8x minus 5 and ug equals 6x plus 13. Why do I know that? It is given. Okay, so now you have all your givens, and now you're going to start, I call that, you got the food out of the fridge, and now you're going to cook. And remember, we're trying to solve. So I'm going to take this mu, and I'm going to replace it with that algebra. And I'm going to take this ug and replace it with that algebra. So I have 8x minus 5 equals, and this is going to be 6x plus 13. You ask yourself, what's going on here? That's, we swapped the segments out and we put in the algebra. So that's called substitution. And I'm not sure if your teacher requires this, but I do. When you say substitution, you need to specify which lines did you use to substitute. And we used lines 2 and 3. So we put together 2 and 3 to get line 4. That's what substitution means. Now, the algebra here is really, really easy. You just have to make sure you do one step at a time. So I'm going to add 5 to both sides. And I get step 5. And that's going to be 8x equals 6x plus 18. What allows you to do that, what's the y? That's called the addition property. Because you add to both sides. Now I'm doing minus 6x. Now I have 2x equals 18. What allowed you to go from here to here? That would be the subtraction property. Property means you do something to both sides. Both sides, both sides. Step 7, of course, we divide by 2, and you get what you're trying to prove. Ta-da! X equals 9. Yay, we did it, all of that. And the reason why is that is called division property, because you divided both sides. And always make sure when you're doing a proof that you actually hit your target. And your target was prove x equals 9. Lo and behold, we have done that. Okay, this is another 2-column proof, so we get lots of space here. We are given GHK is 4x, and we are given FHG is 21x plus 5. And with this given information, we're trying to prove that GHK is 28 degrees. So 28 question mark. So once again, given, implied, freebies, talk through. We've marked our given. What's implied is we have ourselves a linear pair. They share a spine, they make a line. So we know it's implied that these two angles add up to 180 degrees. That's important. So logically, we are going to be doing the two algebras equal 180. You're going to solve for x and plug it in, and you're going to discover, yay, the angle's 28. So all of that is going to look something like this. How? Why? So number one, measure angle GHK equals 4x. I can split the two givens up. I'll put them in one line if I really want to. And I know that's true because it's given. Measure angle FHG equals 21x plus 5. That's true because it's given. So you're like, where do I go from here? Number two, I know that the measure, let's see here. I'm not sure how your teacher wants you to say this. It's not really directly mentioned here. Okay. You need to say something like this. Angle GHK, comma, angle FHG are a linear pair. Linear pair means two angles that make a line. I would simply call that a definition of a linear pair because they share a spine, they make a line. I'm not sure what your teacher calls the next one. I think it's called the linear pair property. So right here, because it's a linear pair, the measure of angle GHK plus the measure of angle FHG equals 180. We would call that, in my class, the linear pair, I'm just putting LP for space sake, property. Number 4, now we're going to start substituting here. So because I have GHK, and that's 4x, and FHG, and that's 21x plus 5, I'm going to start plugging stuff in. So we have 4x plus 21x plus 5 equals 180. And that is substitution. And the lines we used to get that line, we used lines 1 and 3. So both lines 1 and 3 feed into 4. So lines 1 and 3. Now you just have to do the algebra, obviously. And just make sure you do your algebra one step at a time. Collect like terms. We have 25x plus 5 equals 180. The technical name for collect like terms we might run out of space here, is number 5. That is addition / subtraction of real numbers. That's what you commonly call collect like terms. We subtracted both sides. That's called the subtraction property. One, 2, 3, 4, 5, 6, 7. We can say x is now 7. And the reason why, that is division property. And last but not least, because we already have, we're going for GHK. So back up here, GHK is this blue, which is 4 times x. We come all the way down here, and the measure of angle GHK equals 4 times 7, which is 28, which is what we're trying to do. The reason here is substitution. And you specifically used lines for this substitution. We used line 1 and 7. Select all the rotations that will carry the figure onto itself. That means how much, looking at this one, how much do you have to rotate to get the same image? So let me just give you a little crash course. If I drew an arrow like this, to get the same image, I'd have to rotate a full 360 degrees. If I have an image like this, to get the same image, I'd only have to rotate 180, and I'd end up with the same image. So here, to get the same image, you would simply rotate 180. If you rotate 90, just so you can see the difference, it would mean it would be oriented vertically again. Let me see if I can't draw this real quick. Boom, 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 like this. Can you visualize that? Terrible drawer. 11 o'clock at night. Got it. So you know it's not 90 because that's a quarter turn. And you know it's not 270 because that's a quarter turn. You know it's not 3 carried onto itself. So it's either going to be a half turn, 180, or a full 360. Select all the rotations so it wants all the possible varieties there. Transformation. There's 3 main transformations, just as a crash course. If you take something and you slide it, that's called a translation. If you take something and you mirror it or flip it over, that's called like flipping it over, like a mirror. I mean, just kind of imagine that as a mirror. That's called a reflection. And if you take an image and rotate it, Imagine a pivot there. You have a rotation. So translation is a slide, reflection's a mirrored image, and a rotation. So what we get here, we start at T, and we end up at what's called prime T. And take a look at Q and Q prime. Now, originally, this looks like it's a translation, like it's a slide. But if it was just a slide, this is kind of where the tricky part is. If that was a slide, your T prime would be here and your Q prime would be down there. So it's not a slide in this case, it's a reflection. And if you look very carefully, it is being reflected over that line, which is y equals, we're going to assume the units are 1, y equals -1. So in this case, going from the original to, that's called the pre-image and the image, what transformation is happening, it is a reflection over the line y equals -1. Okay, rotating clockwise and counterclockwise. Wow, this is a lot of information for just the first 2 units. To rotate clockwise to the right, okay, to rotate clockwise to the right, so I'm just going to draw a clockwise arrow. You switch the order, and then you flip the sign on the right. To rotate, and these are 90-degree rotations. To rotate counterclockwise, that would be going this way. You switch the order again, whatever it is, you switch it, and then you flip to the left. To rotate 90 clockwise, switch and flip to the right. To rotate 90 counterclockwise, switch and flip to the left. So here, in general, we are, but this is only when you are about the origin. But we're not rotating about the origin here. We're rotating about 0, 2. So we are rotating right here 90 degrees. So for this one, you're going to get out a ruler. Okay, so the rule that I have here on the left is only for rotating about the origin, which is 0, 0. But we are rotating about 0, 2. So this actually takes about 4 steps here. And this is rather complex for your first unit. I'm going to do my best to explain it, given the circumstances, and hopefully you'll find something beneficial here, Esther. Let me just go ahead. I need some space here. Alrighty. So step 1, we're going to get our 3 points. And right here are Z. Notice that's Z, M, and T prime. That's our final results here. So for Z, the original Z, we have positive 1, 1, 2, 3, 4, 5, positive 1, positive 5 for our M. 1, 2, 3, 4, negative 4, positive 3. This is M, negative 4, positive 3. And then we have here T, which is negative 3, positive 1. Okay, there's 2 steps, and we're rotating about 0, 2. That's our rotation point, and we need to keep track of which way we're rotating counterclockwise. All right, step 1. You take the 0, 2, because we're rotating not about the origin, but about that point, and we're going to subtract that point here. So 0, 2, subtract, and we're going to get an internum point here. 1 minus 0 is 1. 5 minus 2 is 3. And again, we're subtracting 0, and we're subtracting 2 here. If this was a negative point, double negative would make a positive. So that's 4 minus 0, that's still 4. 3 minus 2, that's 1. We're subtracting 0, and we're subtracting 2 here. And we get negative 3 minus 0 is 3. 1 minus negative 2 is negative 1. Okay, that's step 1, is you take that point away. You're shifting it. Now you're going to do the switch and flip to the left. So I'm doing 3, 1. So first off, I'm just switching the order. And to rotate, you switch the order, and then we're counterclockwise. You flip the sign on the left. Flip the sign on the left. Flip the sign on the left. If that's negative, it becomes positive. Last but not least, you're going to add back the points. We shifted, we messed with it, and then we're going to add it back. So we're adding 0, 2, adding 0, 2, adding 0, 2, and your final Z prime is going to be negative 3, add back the 0, so it's negative 3, 1, add back the 2, so that's 3, negative 1, add the 0, that's negative 1, that's going to be 6, that's going to be your M prime, and then your T prime, positive 1 plus 0 is 1 and 5. So we're going to take these 3 points. Moving back up here. And we have here negative 3, comma 3 is our Z prime. Negative 1, comma 6 is our M prime. And 1, comma 5 is our T prime. Our origin point was 0, 2. Let's graph these 3 points. And when you connect them, you get your rotation. Let's try another one here. Said, what are the coordinates of y after fjy is translated using this notation? So what we're doing here is we're simply adding 2 to the x coordinate. Adding 2 plus, oh, hang on, that's our multiple choice here. So take these coordinates, and it's asking only for the y coordinate. So your y coordinate is at -1, -1, 2, 3, -4. And it just wants you to add 2 to this, and you're going to get +1, -4, which is answer B. Rewrite the translation 5 units up and 7 units down. In coordinate notation, so in coordinate, you just take the x coordinate 5 units to the right. That's for the x coordinate, so it's going to be +5. 7 units down, that's the y, so that's y -7. So that'd be coordinate notation. And then vector notation is usually represented like this. To the right would be positive, and down would be negative. Disguise the transformation. If you look very carefully, the C moved there, the W moved there, K moved there. So this is just a bunny hop, if you will, and therefore it's a translation. It's not a reflection. So translation. So your translation is simply 1 unit to the left, 1, 2, 3, 4 units up. Just check to see if that's true. 1 unit to the left, 2, 3, 4 units up, 1 unit to the left, 4 units up. So your translation is going to be x -1, comma, y +4. That's your coordinate translation. When this is rotated about the origin clockwise, so to rotate 90 clockwise, you switch and you're going to flip the sign to the right. Let me explain. And it's asking only for the image of P. So P is sitting at 1, 2, 3, 4, -4, comma, 1, 2. And therefore, you first switch the order to -4. And because it's clockwise, you go clockwise and you flip just that sign. So 2, 4. The answer is going to be C. What transformation creates? So you ask yourself what happened here. So it's obviously a reflection. Right off the bat, you can see it's a reflection, not a rotation, so we can cross that out. Dilation means to change in size, get smaller or bigger, and that's not. It's not simply sliding around. So it's either reflection across the x or y axis. You see it's flipping over this way vertically, so it's reflecting across the y axis. Esther, kiddo, this is a lot of information. We should have been reviewing a week ago, so I'm doing the best I can. If we have 48 and -29 and we're rotating counterclockwise, what's that? So to rotate 90 counterclockwise, you switch the order and you're flipping to the left. So first I switch the order, and then I draw a counterclockwise arrow, and I flip that sign. So my 90 degrees counterclockwise rotation is going to be 29,48. To rotate 180, just think of this logically. If I take a point, let's say here, and it's positive, positive, and I rotate exactly 180, the position of that point is going to be the same horizontal and vertical, but it's going to be in the exact opposite quadrant. So all you do to rotate 180 is you simply flip both sides. So if I have negative 53, that simply becomes 53. If I have positive 56, this simply becomes negative 56. So to rotate 180, all you do is flip both sides. Okay, pre-image and image after this translation. Our pre-image, M, is at 0, 4, and V is at negative 4, positive 1, and H is at negative 2, 1. Now, all we're doing for each of these is we're translating 4 units to the right, 2 units down. So the first one, I'm going to bunny hop. So you can see that you could physically bunny hop this if you wanted. So we could just do this. We add 4, 1, 2, 3, 4. Then we go down to 1, 2. There would your new coordinates be. So that's called M prime. That is 4, positive 2. That would be your M prime. Now, mathematically, what's going on here is you add 4 to the x and you minus 2 to the y. So that's what's going on mathematically. And if you did that, you see you get the exact same thing. So we're going to do the shortcut for both. We're going to add 4, minus 2, add 4, minus 2, and then we'll graph it. So our V prime is going to be 0, negative 1. And our H prime is going to be positive 2, negative 1. Oh, hang on. H is sitting at negative 1. So minus 2 is going to be minus 3. There you go. And that's H prime. So positive 2, negative 1, 2, and 3. H prime. And you connect and you have the exact same image. It's just been slid 4 units to the right, 2 units down. Graph an image after rotating 180. When you do something 180, you just flip both sides. But we're rotating about negative 2, 1. So this is where you have to do the add and then take it back and rotate. So first we get our 3 rotations. Negative 3, positive 5. J is at negative 5, positive 4. and Q is at -4, 0. Take this over to a new page so we can see it nice and big. Step 1, we're going to take these points, -3, 5, -5, comma 4, -4, comma 0, and we're rotating 180 about the point. So we first start by subtracting the point from both. We're going to get our what's called our internum point here, which is -5. We're subtracting, whoops, hang on, no, that's going to be a double negative. So technically we're subtracting -2, so your internum point, that's adding 2. So it's going to be -1. This one we're subtracting 1. And so that's 5 minus 1, which is 4. So that's our internum point. Watch out, we got a double negative there. So that's technically -5 plus 2, which makes that -3. And this is -1, makes that 3. Double negative makes a positive, so that's +2, which makes that -2. And -1, that makes that -1. Now, to rotate 180, you simply flip both signs. So we're going to flip this to 1 and -4, 3 and -3, 2 and 1. Now we add back, if you will, the -2, 1. So keep in mind, -2, 1, 2, 1, -2, 1. The adding back, so that's 1 plus -2, that's -1. Let me get our coordinates here. We're now back to our original. And -4 plus 1 is -3, so it's 1 point. You add -2, so technically that's 1. We're adding, that's -2. Adding the -2, technically subtracting, so that's 0, and that's 2. Now let's take these points. And we're going to graph them, and you can see how they look. -1, -3 is here. +1, -2, and 0, 2. So we have been rotated 180. That's pretty easy to see. Now we're going to graph -2, +1. So you can see there's our pivot point, -2, +1. And every single one of these have been rotated exactly 180, about that point. Okay, let me give you a crash course. If you're flipping over the x-axis of anything, all you do is you opposite the y-coordinate. If you're flipping over the y-axis, all you do is you opposite the x-coordinate. So to flip over the x, you opposite the y-coordinate. Therefore, you have -54 and -17. Flips it over the x-axis. We have 4, -6, and we translate 6 units to the right. That just means we're adding 6. And 8 units down, that means we're minusing 8. So 4 plus 6, new coordinates would be 10. -6 minus 8, new coordinates would be -14. That would be your H prime. We are going to take this and we're going to reflect it across x equals 1. So x equals 1 is this line right here. This one might be, it's just easier to reflect this physically. So 2 units to the right, 2 units to the left. There's your n prime. Come down here, 1, 2, 3, 4 units to the right, 4 units to the left, 1, 2, 3, 4. There is your R prime. From here, 1, 2, 3 units to the right, 1, 2, 3 units to the left. There is your V prime. And now you just get those coordinates, realizing that black line is not your axis. This is right here. So your n is technically over 1, over 1, -1, +5. That's your n prime. Your r prime is 1, 2, and that's -3, +4. And your v prime is only 1, 2 over -2, +1, 2, 3. Describe the reflection and rotational symmetry. Okay, first off, reflective symmetry is if you can fold a shape. For example, if I have an equilateral triangle, how many times can I fold it, or where can I fold it and get the exact same image? So I could fold it that way, I get the exact same image. So reflectional symmetry is a folding concept. So I get one folding. So I get 1, 2, 3. So out of an equilateral triangle, I have 3 axes of reflection. And out of an equilateral triangle, rotational symmetry is how much do I have to rotate to get the exact same image. So if I go like this, there's my circle. Circle's 360, which means each of these rotations is 120. So to get the exact same image, I only need, my rotational symmetry is 120 degrees. Now, for the figure below, problem is they don't tell you if it is or is not regular. So we're going to assume it is. And if that is the case, we have 1, 2, 3 axis of reflection. I can fold it on any one of those points and get the exact same image. So far we have 3, but watch out, we could also fold it this way. 4, 5, 6. So for a regular hexagon, there is 6 axes of reflection. As far as rotational symmetry, imagine this is a circle. 1, 2, 3, 4, 5, 6. So it's 360 divided by 6, which of course is 60. So your rotational symmetry is going to be 60 degrees. Describe the transformation below. It's pretty easy. It's going to be a reflection, obviously. 1, 2, 3, 4. Your exact middle is this way. So we are reflecting across that line. And that line is simply x equals 1. So this is a reflection over x equals 1. This is a 90-degree rotation, and it's a 90-degree rotation counterclockwise. Nope, I take that back. That's not a rotation. After a careful examination of the corners, watch the corners. They are not simply rotating. If you color code these corners here, they are butterflying, which is a reflection, and now you just have to try to find the line of reflection. You simply get a ruler here and ask yourself, where does it go to get an exact reflection? And it is right here. If you look really, really, really carefully, it's a very common reflection. We're not reflecting across the y or the x-axis. There's your point of origin. We're reflecting across the line, and this line is simply y equals x. Y equals x, that's a line. Why? Because my slope is 1 and my intercept is 0, so we just call it y equals x. So this one is a reflection over y equals x. Good luck, my dear.